Thank you very much, Federico, for that very kind introduction. The pleasure and enjoyment is mine, and it's my first visit here to IST, and I'm enjoying myself so far. I wish I could stay for longer, but it's I've had a very good conversation with people over lunch and so on, and I'm great honoured to be here and talk amongst so many plasma and other physicists here. So it's great. I've come off a very long plane flight from California, and I'm in a situation where I'm giving a lecture in front of a bunch of distinguished plasma physicists, and I wake up and find that I am. So if something bad happens, just don't disturb me. Okay, all right. Well, thank you very much indeed. The topic I was asked to talk about is the title, really, The Extreme Electrodynamics of Complex Sources. And as Federico says, my colleagues and I have started a collaboration to investigate this sort of general area, which is very much at the intersection of astrophysics and plasma physics and more generally electrodynamics, and I think physics beyond that, and also especially cosmology. So I'll try and make that a little bit clear. It's very much new territory. This is one of the cases I'm going to make, and I'll try and give you a little bit of the flavour of what we're doing, but I don't want to sort of get into the mechanics of a collaboration so much, but I will say a little bit about it. It's Simon's collaboration here, and that's our logo, and that's where I come from in Stanford. And maybe I should go on to the next slide. Will that one do? It's not quite advancing. Okay, maybe we do it that way or that way. Nope. This is not advancing. Sorry about that.
Make one click on the presentation.
Maybe that's what it needed. That's where it goes. And so, yeah, okay. So this just gives you a bit of a flavour of it, and I won't go through everybody is here, of course, but these are just some of the people you'll recognise, some of the names of some of the faces, maybe. And this is the sort of general area, and we obviously we're interested in both quantum electrodynamics and general relativity, and obviously classical electrodynamics, plasma physics, and so on, and the sort of arena in which these are practiced is very much neutron stars and black holes. So we go on. I get there's pictures there, and I just sort of draw attention to Federico here, and so any complaints should be directed to him because he's on our advisory board. Okay, so just by way of introduction, and this is of course classical electrodynamics, expressed Maxwell's equations expressed in units in which pi is set equal to a quarter, and that's a joke, just in case you were confused. Okay, and of course you know infinitely amounts about this, but I'd just like to draw attention to a couple of things. Of course, that this is something that is sort of very much the history of this business, and of course there was Faraday, of course, and then there was Maxwell, and for Maxwell in his treatise and so on, he knew plenty about atoms. He invented a large fraction of kinetic theory. He knew Faraday's laws of electrolysis and could draw the deductions and so on. But still for him, electrical current was a continuous thing, just like water going down the stream or something. And it wasn't really till 30 years later that Heaviside, shown there, invented the Lorentz force, which is obviously, as you most things, named after not the first person to think about, get it right, where, of course, particles became involved, and there were atomic carriers of charge, atoms and ions and so on, and then followed atomic physics, nuclear physics, particle physics, and, of course, especially in this context, plasma physics. And so, and it's this sort of counterpoint, I think, between the continuous view of fields and and current on the one hand, which is sort of extreme classical limited, and the quantum mechanical one, where one's dealing with particles and so on, and going backwards and forwards between those two descriptions is what characterizes a lot of this physics and its applications. So obviously the other side of this story is the quantum electrodynamics. Again, I'm not going to go through all this. You know this too. Photons are relevant. Something that I think everybody does believe, does know about, is that there is a sort of magical field that's enormous by terrestrial laboratory standards, 4 gigateslas. It's a Schwinger field. It's where the spacing of, if you like, the Landau levels in a magnetic field is equal to the electron rest mass, and that's 4 gigateslas. And the point is, in astrophysics, we are now dealing routinely with neutron stars that have measured magnetic fields that are as much as 30 times that, and conjectured magnetic fields that could be as much as 100 times larger than that. So clearly we're not just approaching the QED regime, we're way over it. And it isn't as though physics... We'll come on, the implications that will come on to. Let me say no more. That was the only point I wanted to make. But, you know, we still believe in QED. And just this is again this will make some of this will make a little bit more sense, and I don't want to say any more than just show you some pictures. And there are 4 fundamental forces of physics here, which you know all about, and all of these appear in this story. There's an intersection with all of these in this story. So it is very general, what I'm talking about, but the thing that unifies it is we can't just do this in terms of elementary interactions. This is collective plasma physics that's at work in all of these problems we're talking about. It really is a sort of many-body type analysis that's needed. So let me say a little bit about the two sort of arenas that we have. One of the neutron stars, and the first slide will be a little bit about history that's going on here. They were famously predicted by various people in the 1930s, soon after Chadwick announced the discovery of the neutron, allegedly, and probably really Landau, also Bader and Zwicky famously, and they were certainly taken seriously by Oppenheimer, who's now a famous person, and yeah, he was before actually. And then when pulsars, well, actually before then, people were thinking seriously about neutron stars in the 1960s. They sort of got resurrected in the late 50s and 1960s. And then when pulsars were discovered in 1967, and for me, a slight personal attachment, I was a first-year undergraduate in Cambridge, and I by accident I heard one of the first talks about this because I would belong to the Astronomy Society or whatever it was, and Tony Hewish, who's there, came and gave us a talk about this new discovery, and just been announced, and Franco Puccini and later Tommy Gold made the case that what they were looking at were spinning magnetized neutron stars, and in particular they were responsible for powering this is the Crab Nebula, but much else besides. And so a tiny thing about 10 kilometers across, a neutron star would have a radius of 11 kilometers typically. That is illuminating this big structure here, and as I say, much else besides. They had in retrospect been first seen by X-ray astronomers in 1962 in one particular source called SCO-X1 here, and then they were made manifest in the 60s. In the late 60s, there were gamma ray bursts that were discovered by satellites that were looking for illicit underground explosions and so on the Earth, and they found cosmic sources. And as we'll say in a short while, some of these are neutron stars. And then there are other manifestations of neutron stars. We'll talk a little bit more about some of these. This is just a broad brush picture. There are the what are called soft gamma repeaters. That's shown over here. These are neutron stars that showed X-ray pulsations with periods of order about 5 seconds or so. Every 5 seconds there was, and this was a rather slowly rotating neutron star, unlike the pulsars, which rotate with periods that can be as short as milliseconds. But what was special about these was the magnetic field strengths are these high values of about, well, I don't know, do you prefer Gauss or, maybe do you prefer Gauss or Teslas? Gauss. I heard Gauss. All right. So Gauss. Okay. Traditional. Okay. 10 to the 15 Gauss then. I won't say peta-Gauss because that's kind of a hybrid. Okay. All right. And then there are fast radio bursts. They're now happening about 1 a minute or so over the whole sky. And we'll say a bit more about these too. Those are believed to be many of those are believed to be magnetars. This is a work in progress, not totally convincing the story, but that's the way the evidence is pointing right now, that many of them, if not most of them, are magnetars. These 10 to the 15 Gauss in your units, 100 gigateslas for others, magnetic field neutron stars, and then of course famously the neutron star merger seen by LIGO in 1708-17, that's a date, and explore everything. And these are two neutron stars coalescing, probably making a black hole. And this is down here is the gravitational wave signal associated with that. This is taken again, this whole business into totally new territory, and there's going to be a lot more observations like this very soon. And then there's, say, these fast radio bursts. That's up here. Is one of the discoverers of them. And let's just move on to another one. So it's a little bit more about the physics of neutron stars here, and some of the people who told this story. As I say, a long time ago, I wrote some sort of review of neutron stars, and I think the challenge was to find a part of physics that didn't have some expression on a neutron star or within a neutron star, and pretty well all of physics is expressed somehow or other in a neutron star. So it's combined sort of everything, atmospheres down to nuclear matter in the interior. Typically the masses are no more than 2.5 solar masses. Nuclear density, magnetic fields, as I say, and the magnetars here are 30 times the Schwinger field and could be that high. They slow down because they radiate electromagnetic waves, if you like, at the spin frequency. It's not just a simple vacuum wave, it's more complicated than that, but they do lose energy in a definable way, and they have totally fascinating properties, and you can see manifestations of that in sort of seismic activity. So just like you call this geology on the surface of the Earth, we like to call this astrology. Okay. Okay, and so here's some more recent things going on, and this is one of the points I want to make here from this slide is not to go through every one of these things and just say this is stuff that's happened over the last year. So this isn't sort of historical, these are things that are ill-digested, and people are learning more both observationally and thinking more about what's going on. And so just very quickly, some of the things that are happening here, I won't go through all of this. This was the 1708-17. It makes jets. So you've got these two neutron stars, and you think they just sort of make a black hole, but in fact they make what's sometimes called a kilonova, and those make jets, which you see all over in astrophysics, and these are no exception. You get more jets. This is in the Vela pulsar, and you see it's a spinning magnetized neutron star. It makes jets, and this is a very recent result from an X-ray satellite that does polarization. You see up to 60% polarization in this. That's telling you loud and clear that whatever's going on around it is a giant current flow, a giant magnetosphere of organized magnetic field. This isn't some sort of random turbulent condition. It's the sort of thing you aspire to in a tokamak, a well-controlled current system. And that's a big message for all of these sources. They're able to make giant current distributions with the associated magnetic fields. One's learning a lot about the, as I say, the seismology, if you like, of these neutron stars. I won't go through what all the details are. These are some fast radio bursts, these little flashes that happen with intrinsic timescale spats of 10 milliseconds, and they make flashes, just a flash. Sometimes they repeat, often they don't. And then sometimes these flashes show quasi-periods inside them, which could well be modes of oscillation in the neutron star. Okay, you know, it's all new. This is interesting. Anybody got any good ideas? See me afterwards. Okay, and now black holes, the other sort of star of the show. They, of course, were hypothesized by Schwarzschild, and then again Oppenheimer got the story much righter than many subsequent general relativists, and they were sort of identified in two separate ways, one in retrospect in quasars, and here's Martin Schmidt who identified them using positions from Cyril Hazard and so on, and also in binary X-ray sources. So these are like stellar mass black holes, say tens of solar mass black holes, and these are like, this one is the famous one in M87, which you may have just seen once or twice, this great big orange ring. That's 6 billion solar masses, so that's not the heaviest, but it's getting up there. And this isn't a quasar, but it was once. It was as bright as Vega when it was a quasar, but nowadays it's kind of pathetic, like the rest of us. And but it shone brightly once, and it makes a jet, of course. Both of them make jets, but this is another one from another source, 273, the first quasar. The gamma ray bursts, I associate them with neutron stars. They're also associated with black holes. In fact, most of them are probably associated with black holes, and we see these gamma ray bursts, flashes of gamma ray radiation, and all of this activity, the gravitational waves, and the monitoring of the stars orbiting the mere 4 million solar mass black hole at the center of our galaxy. Don't be ashamed of it. It's only 4 million solar masses. You wouldn't want to live next to a quasar. It's okay to live next to a 4 million solar mass black hole. And there was one set, well, there are more Nobel Prizes, but this is one set of Nobel Prizes for the gravitational radiation, another for doing this sort of thing, and then Roger Penrose. I must admit, when I saw these pictures, I thought, I looked at that one and I thought, okay, so maybe black holes do have hair after all. All right. Okay, another personal thing is when I was a student, I went to a summer school as an undergraduate, just graduated, and here two of the lecturers there, and they were the ones who discovered Cygnus X1. So it's again purely fortuitous. There's, you know, I've been seen from a very safe distance, people making great discoveries. Okay, all right, let's move on. So black holes, so there's a lot that's known about this. Of course, Schwarzschild first sort of wrote down a metric, but the real astonishing thing that was done was by Roy Kerr, who found a solution to Einstein's equations that described what was a space-time, but as far as astrophysics is concerned, it is the space-time for a black hole. And in particular, the original one has no charge, and that's really all you need for astrophysics. If you follow the febrile imaginations of theoretical physicists, then you can go, you can look at many other types of black holes, including those with charge and with other fields and in other dimensions and all the rest of it. It's all good. It's all good. But as far as boring old astrophysics is concerned, all you really need is a black hole that's characterized by spin and mass. Those are the two things. So it's just two. It's simpler than an electron. So it's just two numbers. And the mass is just the scale. So this is Roy Kerr. In fact, I just went to, I went on holiday in vacation 3 weeks ago in New Zealand, first time I'd ever visited there, and I called in to see him in Christchurch, and he's going to be 90 next month, so he's full of ideas. And but it's a really remarkable discovery. John Wheeler, who in the United States founded a sort of school, and then Roger Penrose and Stephen Hawking here, who along with many other people, in very short order, once they got the hang of Kerr solution showed how remarkable it was and how beautifully it all worked out. Now these black holes have one thing they have is they have a region around them when matter has to orbit. It's called the ergosphere. It's outside the event horizon, and that's a special property of a spinning black hole. And they are believed to be seen courtesy of rings of gas around them called accretion disks, and this is what they would look like with the bending of light. And then as a central part of what I'll be talking about here is magnetic fields are there, shown in a cartoon-like way here, and those magnetic fields are really what we think activates them and takes the spin energy and makes them into things that gratify astronomers, observational astronomers, and so on. Okay, so and then here are some recent manifestations, and again I'm not going to elaborate on any of these, there isn't time, but just to give you some idea, this is M87, this is the orange ring, and as I say, it makes jets. And one of the things we've been learning about these jets, which has been known for some time actually, is that you really see them as the walls of the jets, and I may have time to come back to that. There are other manifestations perhaps of black hole. Here's one. Here's a famous source that I've been fascinated by for a long time called SS433. It's a binary source. There's a black hole. It makes jets and they precess every 160 days. You can watch them regular as clockwork. They've got many other periodicities associated with them. It really is a fascinating object. They've just been discovered as high energy gamma ray sources. That was quite unexpected. Here are high energy neutrinos coming from another source, so that's believed to be a black hole. This identification is much less secure, but it's the sort of thing that is out there in the air, and if this one doesn't quite hold up, things like it will assuredly hold up. So this is up to almost a petaelectron volt. So it's a TeV, but it's really closer to several hundred TeV, nearly a petaelectron volt. The highest energy neutrinos that are seen are about 1 petaelectron volt. That's 10 to the 15 electron volts, not tevatron scale or LHC scale. So, and then the cosmic rays, they go up to 300 electron volts. That's 3 times 10 to the 18, or 50 joules in one particle. Okay, takes some thinking about. That's high energy physics, if ever there was. Okay, and so the big puzzle, and then one of the things that's happened recently is that it's part of the story, is that there's a background from that's been measured using pulsar timing, just using pulsars as detectors. You can see this background of what's called nanohertz. That means periods of several years, gravitational waves. It looks pretty real. In fact, I've seen better data than this, and it's right on. This is the prediction. The better data I've seen is much closer to is much smaller error bars. So I think this is real. This background that's been measured. It's a new window on the universe. Gravitational waves. Okay, and this is a phenomenon that happens around massive black holes and galactic nuclei. They make what are called tidal disruption events. A star gets too close, gets ripped apart. That seems to be what's happening in most of these cases. And these again make jets and high energy phenomena. So there's a lot going on in terms of observations and a lot to try and explain, reverse engineer. I'd like to just say a little bit here sort of procedurally or methodologically about history. I mentioned the gamma ray bursts. And again, this won't be a long discourse on gamma ray bursts and the different types and so on, but I would just say that when they first came about, and they were around since the 60s, and then they became fashionable in the 70s and 80s, and there were well over 100 published, not just crackpot, but published explanations of these things. Ruderman, in a talk I actually heard at one of the Texas Symposia, said, well, you can read it yourself, but he regarded this with some sarcasm, but comets of antimatter falling onto white holes had not yet been claimed, but most of the other things had been, and there's some pretty wacky stuff. And so you might say, well, this is all just a good, clean fun for theorists who stop them doing anything more more useful or more dangerous. But in fact, the way it's worked out, and it often does, is that we now see this whole heterogeneous class, and it looks pretty clear that there are three very distinct phenomena that are responsible for different types of gamma ray bursts. And it's not 100, it's 3. Now, there'll be some odd things there. Of course, there will be. This is astronomy. There'll be some oddball things, of course, and misclassified things and new things to be discovered. But basically, most of them are either what are called soft gamma repeaters, which are these magnetars with 10 to the 15 Gauss magnetic fields, and they're having flares like solar flares. Then there are the long gamma ray bursts, which are a type of supernova explosion. A massive star collapses and forms a black hole, and a minority of those make gamma ray bursts. Most don't. This minority do. And then the third type are neutron star mergers, which make a different type of gamma ray burst, and they also make a black hole, but they do it from the merger of neutron stars. And so the story really is that in all this sort of observational confusion emerges a pretty good explanation of what's going on. So if we and so I say now if we turn to the more recent phenomenon, which is only about 15 years old, the fast radio burst, and this could be history repeating itself. Again, we've had this plethora of theoretical explanations. The two that are real, the radio interference and microwave ovens. It turned out that a lot of them happened at lunchtime, and you have to be a card-carrying radio astronomer to understand just how embarrassing this was. Because several of these alleged fast radio bursts where people were cooking their lunch. And but the rest of them come from the other side of the universe. And there again we had alien light sails, strings, quark nuggets, you may recognize all these sort of things, ball lightning, everything like that. And so, but it's looking like a lot of them actually are magnetars, and it's only circumstantial evidence right now. There could well be 3 different types. I mean, don't know that there are, but some of them are really associated with regular pulsars, but not all of them for sure. And so we're at an interesting stage in the development, but I have some confidence that within 5 years, say, we'll all be more or less agreeing what most of the fast radio bursts are. And certainly the field of seriously discussed candidates and conferences on this business has narrowed considerably over the past 2 years. And so I'm not hearing a lot more about entangled molecules, etc., etc. Okay, all right. Now, so some general things for the physicists here, and this is kind of a popular talk, but I think it's a popular side, I mean, but it's basically, old-fashioned astronomy is just optical. It's just 1 octave. You just, it does go like that. And but there's 140 octaves out there, half of them in electromagnetic spectrum, all the way from low frequency radio waves, high energy gamma rays, all the way up there. And then we have cosmic rays, neutrinos, and gravitational radiation. Maybe one day we'll have dark matter on this slide. I don't know. It hasn't appeared there yet. But these are all. There's a lot there to observe, and so it's not surprising that people make discoveries. And so I then like to sort of just, as I say, we call this, the word extreme is being applied as an adjective to electrodynamics, and the extremity is along several different axes, and that's the thing I would like to get out here. And I think it is interesting. I mean, there's. I don't know, people know about the Guinness Book of World Records. Some people aspire to do that. It's kind of an interesting story. It was Guinness, of course, they make beer in Ireland, and it was a sort of marketing thing, I think. It was invented by an engineer, curiously enough. And they wanted to have people in pubs have a reference so that when they argued about things, they would they do this in pubs, and they use the Guinness Book of World Records to say which was the biggest animal or whatever. And so this has obviously grown a little, and they're great advertisers. This is an early one. And so I think there are several entries here. Some of them have actually made it into the Guinness Book, most haven't. black hole mergers, they're pretty powerful, 10 to the 49 watts. I mean, that's a lot. A gamma ray burst is a mere 10 to the 45, and then a quasar, which used to be the brightest thing in the universe, blah, 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 is now a mere 10 to the 39, so 10 orders of magnitude less than that. But, you know, these are fantastically powerful compared with, say, the sun or something like that. So this is pretty powerful. If you take, is that what I wanted to do? And yes, sorry, I think I missed one out. Did I? Yeah, that's right. This is it, energy frontier. So I'm saying just in terms of the particles you're looking at, so I already said this, the ice cube, this is this facility in Antarctica that sees the high energy neutrinos. They're petaelectron volt, 10 to the 15 electron volts. And the highest energy gamma rays, and the facility I've actually visited I've never been to the South Pole, but I've been to Western Sichuan and seen LASSO, and it's spectacular. In many ways, and that's the same comparable energy gamma rays it's seeing up to those energies. And again, the facility isn't finished yet, but I mean it's already observing, and it's doing fantastically. And then there's the high energy, ultra high energy cosmic rays. Two facilities, one in I visited both actually, one in South America and the other in Utah in the United States. And again, and there are other facilities, certainly associated with European groups, and again, they're up to 300 extra electron volts, 50 joules. So that's really energetic, and so one's learning a lot there. And then I think in terms of thermal frontier, my friends and colleagues who work on superconductivity, they're always talking about high TC, and I say, well, we've got 10 billion degrees Kelvin. What do you make of that? And they slink away. And I mean, I'm impressed by laboratory high TC, but this is something different. And you're talking about somewhat analogous physics when you do this, and of course superfluidity and so on. And then there's another way of thinking about this, which I think is kind of got a message in it, and that is if you consider these fast radio bursts, and you can associate a temperature with them, just as you can with any wave. You just ask how many kT there is in a cubic wavelength. And that'll come out to about 10 to the 40 degrees Kelvin. So you're in the same sort of rate. If you do the same sort of thing through a tsunami, you get the same sort of, it's a bit less than that, but not a lot less. A big tsunami is about that order. And the point I would make here is that oceanographers don't study tsunamis by exploring the private lives of water molecules. They don't sort of say there's a hydrogen bond here or something like that. They do continuum mechanics. I mean, that's what they do. They don't even worry about viscosity, to be honest. They have turbulence and so on, so they don't really worry about viscosity. Aerodynamics is the same. And so that's, I would argue, is the place where, when we're trying to understand these cosmic phenomena, we should be thinking about them more in terms of continuum mechanics rather than bottom-up electrodynamics using electrons and protons and positrons and all the rest of it. Okay, so that was the point. Okay, then there's this observational frontier. There's telescopes coming, being deployed, coming soon. There's a mixture here. I've talked about some of them. I'm not going to say any more about this. Just say there's a lot of telescopes. End of story. Okay, those who think the only true astronomy is cosmology, it has a big interface with cosmology too. Obviously, the kilonovae I mentioned. There's if you care about jewelry, the good stuff comes from these kilonovae. The cheap stuff, like zirconium, that comes from other stars. But the platinum and the gold and so on, and the silver, that all comes from these kilonovae. So it's good. The active, and then you can use these as cosmological measurements for measuring the baryons. They have a huge role to play in the narrative history of galaxies and how galaxy formation happens. And then the nanohertz gravitational radiation. There's much more going on. So there's a strong interface there with cosmology. And then observationally, a lot of the universe, a lot of this, say petaelectron volts, you can't see very far in gamma rays. You can see neutrinos across the universe, of course, but the gamma rays you can't. They're absorbed very close to home. And we believe in QED, and this is actually turning out to be very interesting because you're pushing right up against its limits with well-known processes that are not controversial. Okay, and then again, I'm not going to say much about this at all because the people here who are great experts on this, I sort of work vicariously in this business, sort of with other people like Federico, Silva, and so on. Put an old Osiris simulation here. There are much of the theory here is transacted in terms of simulations, and the simulations are mostly, not exclusively, nowadays sort of particle in cell type codes and things like that are sort of bottom up and teaching us a huge amount about the way that plasmas actually behave in a collective way beneath the surface of a neutron star and in many other environments. And a point I would like to emphasize very strongly is the convergence, not just in terms of technique, but in terms of people, the convergence between what you do to try and interpret or plan an experiment and what you do with an observation. The similar codes are being used, similar people are working on both problems, and they can be used, both communities can learn from each other. And I think one sees that very clearly here. That's been very much part of the philosophy here at IST, but I think more generally that message is getting across. Okay, where are we going? Oh, and then experiment, okay. Lot going on that's taking you out into the Schwinger regime. LCLS2 is Slack, where I work part-time. Here's the NIF in Go, and then IPFN. So all these things, there's a sort of convergence of the experiments and the observations taking you into related, not the same territory. There are important differences, but there's a lot of overlap in terms of physical conditions. Okay, and then if I go to my last frontier, it'll be the electromagnetic frontier. Here I said the field strengths of pulsars were a mere 10 to the 12th Gauss. All right, 100 megatesla. That's still pretty impressive if you work with NMR or something. And if we go to, but if you go to the magnetars and maybe below the surface, we could be up to 10 to the 15 or even 10 to the 17 Gauss. Another way of thinking about the extremes is if you ask about, we've got spinning conductors here, including black holes. They make voltages, EMFs, however you want to express it. They can be up to as high as 10 to the 23 volts, and that's 300 times as the minimum you need to accelerate the highest energy cosmic rays if they were protons, and they're almost certainly not protons, so you're probably 10,000 times more than you need to accelerate if they're ion nuclei, accelerate them. And so, but you can get that higher voltage. Something like M87 has a mere 10 to the 19 volts, but it too, something like that is marginal for accelerating the highest energy cosmic rays, because assuming that they're heavy particles as they seem to be. So that's another extreme, and the currents are 10 to the 21 amps. So if you're building an accelerator at CERN or something, then this is an impressive current. Okay, and of course plasma physics is essential to all of this. So at this point I've got more stuff to talk about. Can I get some guidance as to how many hours I should go on for?
Between 5 and 10 more minutes.
5 and 10 more minutes. Okay, then I shall do everything extremely fast so no one will understand it or question it. Okay, so let me just try and get some top level things, and then I've got sort of more slides, and then in the discussion some of these topics may come up. So I'm sort of drilling down a little bit deeper and a little less general. I'm drilling down deep into one of these topics. So I think, look, wearing my astrophysics hat rather than theoretical physics hat, I think one of the questions is, what are the main metabolic pathways? You know, when I was a postdoc, I worked with Jerry Oestreicher, and it was the time of Watergate, which was a big American scandal, and the catchword was follow the energy, follow the money. So he used to say, no, in our business we follow the energy, and I would say it's even more general than that. We follow not just the energy, we follow the matter and the angular momentum and the current as well. But it's basically these giant conservation laws. Follow them. Where does most of whatever it is go? What are the pathways? And if we want to know in terms of energy, we've got gravitational energy, rotational energy, electromagnetic energy, and neutrino energy. And those all are players. They all feature in our attempts to understand these objects. But understanding which of them are important and where is one of the big challenges. And I would say this is probably mostly understood for pulsars, quasars, soft gamma repeaters, and so on. But in the case of the gamma ray bursts and the fast radio bursts, and more generally active galactic nuclei, there are very big questions there. Okay? So I'll just say that. So I take a second sort of top-level question is, how are the highest energy particles accelerated or created? So I'm talking here about the zeta electron volt, 10 to the 21 electron volt cosmic rays, the neutrinos and the gamma rays. What are the mechanisms for getting you into the Guinness Book of World Records? What is actually going on? And there is interplay between that and what facet and things like that. There's historical people working on both problems have learnt from each other. I've learnt from both problems. So you can do direct acceleration. You can do things stochastically in shock fronts. You can have current sheets, or you can invoke highly exotic processes using quark nuggets or something like that that are decaying. All of these have featured. So this is the top level question. And some of this I think we're starting to have answers, others less so. So it's interesting. So the third top level question is there any evidence of physics beyond standard electrodynamics? I believe in Maxwell's equations. I believe in quantum electrodynamics. There are people out there who say, well, there could be more there. At the very least, it's worth testing. It's worth looking for new effects to see if there's anything. I see no evidence as yet for anything that sort of says, I'm really worried, QED's wrong or whatever. I see no evidence of that, but it is still worth doing. And the place to look, obviously, is when you're above the Schwinger field. There are things going on. There's the possibility of finding axions in magnetars. That's a very active field right now. It's quite possible you can use them or use magnetars to set limits on this. And then there's no shortage of theoretical physicists who wondered about firewalls and so on around black hole event horizons. No evidence for any of that, but well worth thinking about, well worth considering. So that's again. And so I'll just outline just some debates here, and I'll do this in a few minutes, and we can return to these points if people are interested, and we talk about them perhaps afterwards. The first debate is these are just perhaps a little bit more idiosyncratic to my own research, but I think it's important. How is M87 actually paired? And this comes back to the first top level question. And the standard view is its accretion, its gravitational energy. The gas falls in, spirals inwards, releases its gravitational energy, and that's where the power comes from. Contrariwise, I would argue quite differently that what is happening is the whole thing is powered by the spin of the black hole. And that spin energy is extracted electromagnetically. Not only does it make these jets, these famous jets associated with M87, the very first jets that were discovered in 1918, but they also powers all of what's going on in the disk. And in fact, the gas that's supplied is all blown away in this story. Nothing really gets onto the black hole in this stage in its evolution. That's a very different view. Fields are much stronger. The whole electromagnetism is quite different. It's distinguishable in many ways. One of the ones that's particularly interesting, again, it's an old idea I was interested in, is if you have, because the fields are so strong, the emitting elements cool very fast, you make little sparks all the time. There's optical caustics there. You get little flashes, you get little twinkles. And that should be there in the data, which already exists. So very excited about the possibility of doing that. There are also polarization implications. So here's a second theoretical debate, and I say it's one that which there's much activity going on. I have a very strong view, which others do not share. This is what makes the debate, is what happens when the Lorentz invariant b squared minus e squared changes sign. The standard view is that everything just breaks down. You get just a huge burst of electrons and positrons and gamma rays and so on. It's just a catastrophic breakdown. I would say it's a little bit more gentle than that, and what happens is that the evolution is such that you make an electromagnetic turbulence where you're just about this limit, and you make a transition to turbulence. There are various applied mathematical reasons for saying this, and I would say this is what is actually going on in fast radio bursts and pulsars. is something like this. It's really describable essentially by continuum mechanics, not by electrons and positrons and gamma rays. A very different philosophy. We'll see. This is again a work in progress. And then theoretical debate number 3 is, are shocks cleverer than us? We observe supernova remnant shocks, accelerating cosmic rays up to peta-electron volt energies. Something's got to accelerate them up to zeta-electron volt energies. And my colleagues and I would argue that this happens in shocks surrounding giant clusters of galaxies, and it happens hierarchically, as that the highest energy particles from here, from the supernova remnants, go to the galactic winds, go to the cluster accretion shocks, and that's where these highest energy cosmic rays come from. They may also come from jets. There are other possible sources. That should be interesting. But the simulations of shocks don't seem able to produce this, but maybe they're cleverer than we are, and maybe there are tricks they can perform that we don't know. So that would be that. And then here is a summary of the things that I've tried to say in this talk. And as I say, I can talk more about these topics if you want. I won't read it all out. But I will say this, and I will say obrigado y gracias to you all. Thank you very much indeed.